Hello everyone, my name is Bo-Bo Wei. I'm from the Shenzhen University. I will introduce my work is about the phase transitions and entanglement from the density functional theory perspective. My work was supported by the National Science Foundation of China and the startup funds of Shenzhen University. We know that phase transitions, which is defined as some physical observables, which becomes non-analytical as the control parameter changes, for example, the temperature changes or the magnetic field changes. To study phase transitions, we employ the statistical mechanics. We know that this many-body system, at the thermal equilibrium everything was determined by the free energies. And Aaron Franz classified the phase transitions according to the non-analytical behavior of the free energies as control parameter changes. Then a natural question arises is, how does this non-analytical behavior of physical observables connected to the non-analytical behavior of free energies? This is our motivation, in particular for quantum many-body systems. We study a simple many-body system with Hamiltonian h equal to h0 plus lambda h1. We assume h0 and h1 does not commute. First theorem, we prove that the thermodynamic equilibrium state of this many-body system, which is in thermal equilibrium with a heat bus at fixed temperature T. This density matrix is a universal function of the first derivatives of the free energy with respect to temperature and the first derivatives of free energy with respect to control parameter lambda. This was achieved by two lemmas. We proved this equivalence rows. The density matrix is equivalent is one-to-one map to the temperature and the parameter, and also one-to-one map to the entropy and the H1 density set. And this is equivalent to the free energy derivatives. And then an immediate consequences of theorem 1 is that if we calculate the expectation value of any physical observable, we will find that the first derivatives of the physical observable is proportional to the second order derivatives of energy with respect to the parameters. For example, temperature, this is the second order derivatives of the temperature. And for any other control parameter lambda, which is also have this correspondence. So the free energy non-analytical behavior will transport to the non-analytical behavior of the control parameters for this general quantum many-body system. And also we studied the entanglement measures of this quantum many-body system. We know that all the entanglement measures are defined according to the reduced density matrix. And we show that the reduced density matrix elements can be expressed as some expectation values of some observables. Then, because the density matrix is a universal function of the first derivative of energy, then these mixed elements are also universal function of the first derivatives of energy with respect to temperature and the first derivatives of energy with respect to control parameter lambda. Then this will result in that our theorem 2, we prove that any entanglement measure of this system is also a universal function of the first derivatives of the free energy with respect to temperature and the first derivatives of energy with respect to control parameter lambda. Similarly, we prove that the first derivatives of this entanglement measure with respect to temperature is proportional to second order derivatives of energy with respect to temperature. And the first derivatives of the entanglement measure with respect to the control parameter lambda is proportional to second order derivatives of the free energy with respect to the control parameter lambda. Then here's a summary. So we proved that this general many-body system with Hamiltonian h equal to h0 plus lambda h1, h0 and h1 does not commute. The density matrix, equilibrium density matrix, and also any entanglement measures are universal functions of the first derivatives of free energy with respect to control parameters. And these relations are rigorous. There's no any approximation for these systems, and so they can applicable for many systems. For example, for any interacting spin models, no matter how large the spin is, how big the system is, and also applicable for the interacting bosons in lattice or interferometers in lattice, and even their mixtures. This is the end of my talk. Thank you very much.